In this video, we're going to talk about another technique that helps with use substitutions. So consider the integral quantity 7x plus 2 all raised to the 12th power. Now we know that we could expand out this exponent and use power rule to evaluate the integral, but it's a lot faster and easier to use a use substitution. In this case, our inner function is the function 7x plus 2, and the outer function I'm thinking of is the being raised to the 12th power. So let's let u equal 7x plus 2. Then du is going to be equal to 7 dx. And the problem with this is that we don't have 7 just hanging out as a factor that we can use to instantly be able to create this du. In order to deal with this, an easy way is to just multiply by a clever version of 1. So I'm going to multiply this integral by both 7 and 1/7. That doesn't change the value of the integral, but it does create the value that we need to be able to convert our dx into a du. So now that I've multiplied by 7 and 1/7, I see that my du is 7 dx. I can take this piece and this piece and combine them together to make the du that I need. And the whole quantity within the parentheses, the inner function, becomes u. And the 1/7 just remains up front, the integral as the same value. Let's go ahead and integrate. This is an easy thing to integrate. We can use power rule. I raise u to the 13th power and multiply by 1/13 as the coefficient up front, plus c. And in my final step, I multiply 7 times 13 is 721. And I need to convert the u back into x again. This is a common thing to forget, but because our original equation was in terms of x's, we want to make sure that we can convert our variable u back into the original variable x. So this is one way of thinking about dealing with constants. The reason why we are allowed to do this is because 7 is just a constant. Multiplying by 1/7 and 7 doesn't change the value of the integral at all. This technique doesn't work when I try to multiply in variables, so you have to be careful. If your variable is missing, multiplying in a variable actually affects the value of the integration. So let's look at this problem again, and I'm going to rewrite it in a slightly different way. Not everybody approaches this type of constant adjustment in the same way. I'm going to do the same integral. It's going to have the same u substitution, but in this case, instead of multiplying by 7 and 1/7 into the original integral, I'm instead going to do some algebraic operations to my du. Here, if du is equal to 7 dx, that means I can divide both sides by 7, and I get 1/7 du is equal to dx. This is another way of thinking about it. Now, when I go back to my original integral, I'm going to take this dx and rewrite it as 1/7 du. And again, remember that u is the inside thing, inner function, and I get u to the 12th. So this is just another way of thinking about the same technique that we did over here. I like this left-hand side more because it's less likely that you're going to do this in a situation where there was a variable involved, whereas here you could see yourself doing algebraic manipulations by maybe dividing an x by both sides, which actually affects what the du value would be. So let's finish the integration. It's going to be the same steps as before. When I integrate, the 1/7 stays as a coefficient out front. I raise u to the 13th power and multiply it by 1/13 plus c, and we get the same value as before, 1/721 times 7x plus 2 to the 13th plus c. Let's look at another problem that's also a little bit more difficult. X times secant squared of x squared dx. The first thing that I want to do is identify, is there a composition of functions? Is there an inner function and is there an outer function? And in this case, secant squared of x squared, the inner function is x squared, and the outer function is secant squared. So immediately I can think to myself that an easy u substitution would be allowing u to be x squared, and that means that du is going to be the derivative, which is 2x dx. And thankfully we have an x sitting right here, but again, there's this 2, and we're going to have to adjust the constant. So in order to get a 2, I'm going to rewrite this by multiplying it by 2 and 1/2. I'm not affecting the value of the integral because I'm just multiplying by a clever version of 1. Secant squared dx. And now that I've done that, I see that I have all of the pieces that I need to be able to create a du. So together 2x dx becomes du. And I'm left with the integral of 1/2 of secant squared u du. And we're left in another conundrum. Now I need to know, how do I integrate secant squared? And the way to do this is actually to think back of a derivative fact from calculus 1, that the derivative of tangent is secant squared. And using this fact, we can apply the fundamental theorem of calculus part 1. If the derivative of tangent x is equal to secant squared x, that means that going backwards, the integral of secant squared x is going to be equal to tangent x. So integral in this case is 1/2 tangent u, whoops, and the du goes away and becomes plus c. And the variable is different, but the thinking is the same. Notice that this secant squared becomes tangent x. I'm not doing a u substitution. I'm not worrying about variables. And in our final step, we don't want to write this as u. We want to be able to convert back to our original function. So I get 1/2 of tangent of x squared plus c. That's my final answer. And if you'd like, you can always take the derivative of this and see if you get back your original function. The final example that I want to do is actually a non-example. Let's consider the integral of x cubed times the sine of 3x dx. Just like before, I'm going to identify, is there a composition of functions? What's the inner function? In this case, the inner function is 3x, so I'm going to let u be equal to 3x. That means that du is going to be equal to 3 dx. Notice that I don't have a 3 sitting out here, but that's fine. We know how to compensate for that. I'm going to multiply my original integral by both 1/3 and 3. And I have all the pieces now that I need to create a du. So the 3 and the dx together are equal to du. And I end up with the integral of 1/3 x cubed sine of u du. But wait a minute, I can't quite integrate, right? Because although I've changed this 3x into a u, I still have this x sitting here. In order to integrate, all of my factors have to be in terms of u. So let's convert this x cubed into a function of u. How am I going to do that? I'm going to use this relationship right here. I don't know what x cubed is initially, but I do know that u is 3 times x. So I can algebraically divide both sides by 3, and then cube both sides. 1/3 cubed is 3 to the 3rd is 27. U cubed is equal to x cubed. So this additional conversion tells me that I can rewrite my integral as 1/3 times the integral x cubed is 1/27 u cubed times the sine of u du. Nice. We now have everything all written in terms of u. For our final step, we would want to integrate. It's tempting to integrate each piece of this product, to just integrate the u cubed piece and also integrate the sine piece. But that's not how integration works. Just like with product rule for derivatives, we can't just integrate each piece, each factor within a product. So integrate each factor in a product. And what does that mean? It means that this integral actually can't be solved using the techniques that we know. I wanted to give an example of something. We've done all these really nice u substitutions, and it's not always the case that u substitutions are going to work. This is one in which the u substitution gives us something. It turns out we can only integrate this using integration by parts, which is a technique that we'll learn in later sections. So this is not solvable by u substitution.